Welcome to example 1C and D. So in part C, we have a round disk that is rotated at, well, we don't know which way it's going to rotate actually. What we know is that we have a 10 Newton force being applied here tangentially, a 9 Newton force being applied here tangentially, and then a 12 Newton force here also acting at 30 degrees to the horizontal, but it's also acting tangentially. So we're asked to find the net torque, and so the net torque is really the R moment arm, which is A or B, depending on the situation, multiplied by the force, multiplied by the angle between the arm and the force. So if we call this, say, for example, force 1, then R1 will be 10 centimeters. So let's do that. R1 times F1 times the sine of the angle between this arm and that force, which is actually 90 degrees. It's not 30 degrees, as one might get mistaken. The 30 degrees is just there as extraneous information. So we have that torque. That's going to be producing a counterclockwise torque, so that's positive torque. Then we have these two torques, which are actually clockwise, so they're considered negative torques. So we have, let's call that force 2. So minus R2, which would be this distance from here to here, that would be R2. So R2 times F2 times the sine of the angle between the arm and the force, which is again 90 degrees. And then we have this force here, or F3, and that arm here, we'll call that R3, and again, that's 90 degrees as well. So we have minus R3 times F3 times the sine of the angle between those, that's 90 degrees. So now let's go ahead and plug in. R1 would be 10 centimeters, but we need to put that into meters, 0.1 meters, multiplied by the force of 12 newtons. Sine 90 is 1. R2 is a distance of 20 centimeters from the center, so we'll put that as 0.2 meters, multiplied by the force of 10 newtons, and the sine of 90 is 1. And then lastly, R3 is again a distance of 0.2 meters, but the force now is 9 newtons here, multiplied by sine of 90, which is 1. So go ahead and put that into your calculator, and I get an answer of negative 2.6 Newton meters. And the reason why it's negative, that indicates that you're going in the clockwise direction. So that is the direction of the net torque. Okay, now moving on to part D, which we have a beam being pivoted about that point. So this is your axis of rotation. Just over here, O was the axis of rotation, but now for this beam, it's going to be rotated about here. So let's label these forces. We'll call the 60 Newton force F1. We'll call the 50 newtons F2. And then we'll have, I guess this one up here, we'll call that F3, the one at 80 newtons. And then the 70 Newton force, we'll put it as F4. So we're going to be doing the net torque about this pivot point right here. And first of all, if you look at all of these forces, there is one force that is not going to produce any torque. Can you guess which one that's going to be? Hopefully you're realizing if you were to pull or push at the pivot of, say, a door, you're not going to open up the door because there's not going to be any torque because you don't have any distance away from the pivot point. So when you, for example, plug this in here, you'll have R1 times F1 times the sine of the angle, but R1 for this case is 0. So there's no net torque produced from the first one. If we look at the next one, F2, we have R2 times F2 times the sine of this angle, which is 90 degrees. Okay, and R2 will be this distance right in here. That will be R2. That will be 0.2 meters. And that's going to be producing a torque that is going to be making this rotate this direction, which is really a counterclockwise direction. So that's actually a positive torque, not a negative torque. Torques that go counterclockwise are positive, and torques that go clockwise are negative. Moving on to the F3, again, that's going to make this beam rotate in the counterclockwise direction. So this next torque from force 3 is also positive. So we have R3 multiplied by F3 multiplied by the sine of the angle. In this case, it's not 90. So if you look at this, the R3 is from all the way here to here, from the pivot point right to this point where the force acts. And the angle that's formed between this vector and the force vector, That's this angle right in here. That's 30 degrees. So sine of 30 degrees here. Lastly, we have the torque produced by force 4, which is causing it to go clockwise, and that's our negative torque. So we have force 4 multiplied by R4 multiplied by the sine. In this case, it's going to be 90 degrees. And the distance here for R4 is going to be from the pivot point really over to here. That's R4. And if you can look at that, that's 0.2 plus 0.6. It's going to be 0.4 meters. So now let's go substitute in. Remember, the first one's 0. So the second one, we have R2, which is 0.2 meters multiplied by the force 2, which is 50 newtons. And the sine of 90 is 1. Then we have R3, which is going to be the distance from the pivot point all the way to the other end. That's 0.2 plus 0.6 plus another 0.2, which gives us 1 meter, multiplied by the force of 80 newtons. And the sine of 30 is 1/2. Then we have our other torque that's negative. F4 and R4, that's a 70 Newton force, and R is going to be only 0.8 meters. And multiplied by the sine of 90 degrees. Sine of 90 degrees is just actually 1. So our final answer is going to be negative 6 Newton meters. Again, we get a negative answer, which indicates that this beam is going to be moving around in the clockwise direction. So this is clockwise. And that's it for this example 1, C and D.